Hello everyone. This video is titled Using the Laplace Transform to Solve IVPs or Initial Value Problems. Now these are going to be specific, very specific IVPs in which the initial conditions are evaluated at t equals 0. And you'll see why that is when I get into the first page of this video. The first page I'm going to talk about the Laplace transform of the nth derivative of a function, which I'm just going to write out the formula for you. I'm sure in most texts you'll see the development of this formula. I would recommend obviously you read this, but for right now I'm just going to have the formula up here. So if we're given some function f of t or y of t, but here I use f. When I get into the differential equations it'll be y. The Laplace transform of the nth derivative of f with respect to t is the following expression: is s to the nth power times capital F of s. Now capital F of s is just the Laplace transform of the original function f of t. So it's s to the nth times the Laplace transform of little f, capital F of s. Then a bunch of subtraction where in each term the power of s decreases, and then you have here f of 0, the function f, little f evaluated at 0, then it keeps going up, f prime, up in derivatives, f prime of 0 all the way up to the n minus first derivative evaluated at 0. You don't get to the actual nth derivative again. So one more time, the Laplace transform of the nth derivative of f with respect to t is s to the nth times capital F of s, the Laplace transform of little f, minus s to the n minus 1 times f at 0, minus s to the n minus 2 times f prime at 0, and so on, so on, so on, all the way down to minus the n minus first derivative of f evaluated at 0. So hopefully you see from this why the initial value problems we can solve with Laplace transforms will involve initial conditions, where the function and its derivatives are evaluated at 0 only, because those are the only things that show up in this function and its derivatives evaluated at 0. Alright, so let me show you how we're going to use the Laplace transform, and also you're going to also be finding the inverse Laplace transform, to actually find the function. Let's use the Laplace transform and its n inverses to find the solution of certain initial value problems. Now I'm going to go over, I have a few examples here, some first order equations, some second order equations, and no higher than that, but just know that you could apply this method to third order, fourth order, and higher equations. Okay, so here we're asked to use the Laplace transform to solve the given initial value problem. So I have, y is a function, now the independent variable is t here. Y is some function of t. So we're trying to find, y of t that satisfies this equation and this condition, right? The value of y at t equals 0 is 0. Alright. So yes, I know that you could probably solve this in some other way. This is a linear first order equation in standard form. Yes, it's non-homogeneous, but I could do integrating factor here. This is also separable. So again, you could solve this. You could do this in some other ways, but I'm going to do specifically using Laplace transforms. All right. So first, I take the Laplace transform of both sides. So that's the Laplace transform of, and I'll just write this as y prime minus y equals, the Laplace transform of 1. Alright, using the linearity property, this is the Laplace transform of, the first derivative of y with respect to t minus the Laplace transform of y. And then the Laplace transform of 1, again, I'm hoping you've seen other previous videos on Laplace transforms. You should have a lot of these things memorized probably by now. The Laplace transform of 1 was just simply 1 over s. And then I had the little formula for the derivative earlier. Now, instead of f, it's y. Okay, instead of f, it's y. So the Laplace transform of the first derivative of y would be, this would be s times, and then, instead of capital F, I'm going to use capital Y for the Laplace transform of little y. Okay, it's kind of a common convention. So s times y of s, and then minus, and then, s to the 0 times y of 0. And then that's as far as you go, because, the next thing would involve y prime, but I don't want to give it to y prime. So that's the Laplace transform of y prime. It's s times, the Laplace transform of little y of t, I'll call it capital Y of s, minus the value of y at 0, which is 0, and I'll put that in a little bit. And then again, minus the Laplace transform of y. I'm just going to write this off to the side here. This capital Y of s is the Laplace transform of little y of t. Right. So this is also capital Y of s. Right, this Laplace transform of y. Right, then this equals 1 over s. Okay. Now, as the initial conditions come into play. All right, we know that y of 0 is 0, so this is 0. All right, y of 0 is 0. No need to write it. All right. So now I've done the Laplace transform of both sides. Next, we solve for capital Y of s. Solve for this what's the Laplace transform of little y of t? Well, hopefully you can see over here I can factor out capital Y of s, and then I'd have the quantity s minus 1 left over, and this is equal to 1 over s, and then I divide by s minus 1, putting s minus 1 in the denominator with s there. And so we have y of s equals 1 over s times s minus 1. And now that I know what the Laplace transform of little y is, I can find little y. I can find the solution to the initial value problem by taking the inverse Laplace transform of both sides. So doing the inverse Laplace transform. Now the inverse of the Laplace transform of y would just be y itself. So we'd have y of t on the left equals whatever the inverse Laplace transform of this other side is, 1 over s times s minus 1. Okay, and I just had a video out before this, again, if you've been following, watching what I've been doing. If not, read up on it or whatever, where I've done, inverse Laplace transforms. This one's going to involve partial fraction decomposition, right? 1 over s times s minus 1. I do the partial fraction decomposition. This would be some constant a over s plus some other constant b over s minus 1. And then multiplying through by the denominator, I'd have 1 equals a times s minus 1 plus b times s. And so, you could equate coefficients on both sides or replace s with certain values. If s were 0, this would be negative a equals 1. So a would have to be negative 1. And if s were 1, this would just be b equals 1. So a equals negative 1, b equals 1. And so what I'm doing here, using the linearity property of the inverse Laplace transform, this would be negative 1 times the inverse Laplace transform of 1 over s, and then plus 1 times the inverse Laplace transform of 1 over s minus 1. And again, I'm assuming that you've seen stuff like this by now. Now the inverse Laplace transform of 1 over s minus a was e to the at. So this is just e to the 1t. So y of t, then a state solution. Once we've got this inverse Laplace transform, that's the solution of the initial value problem. Equals e to the t, and then the inverse Laplace transform of 1 over s was just 1, so minus 1. Okay, so negative 1 plus e to the t minus 1. There's the solution of the initial value problem. All right, and let's double check it. If you want to check it, just go back to the equation. All right. The derivative of this would be e to the t minus this. The e to the t's would cancel, and you have plus 1, you have 1 equals 1. So this does satisfy this equation. And y of 0 would be e to the 0 minus 1, 1 minus 1 is 0. It satisfies the equation, it satisfies the initial condition. This is a valid solution. Okay, so again, the steps are, 1, take the Laplace transform of both sides. And again, you got to keep in mind this Laplace transform of the nth derivative formula. And then use the initial conditions to simplify things. Then you're going to solve for capital Y of s, solve for that, what is the Laplace transform of the little y of the solution, and then take the inverse Laplace transform to actually find the solution. It's those same 3 steps every single time. Okay, so let's do that again. So I have here another first order equation. This one's again something you could do without Laplace transforms, but I do want to practice using Laplace transforms and solving these initial value problems with them. And again, notice that the initial conditions are evaluated at 0. So those are the only kinds that you're going to be able to solve with a Laplace transform. Alright, so 1, again, I do the Laplace transform of both sides. And then I'll just use the linearity property right now. So that'll be the Laplace transform of y prime plus 6 times the Laplace transform of y equals the Laplace transform of e to the 4t. Now, remember this is from that that first page I showed you in this video. The Laplace transform of y, the first derivative of y would just be s times the Laplace transform of y, which again I'm going to call capital Y of s, minus, and then s to the 0 times y evaluated as little y evaluated at 0, right? Which I'm going to get from the initial condition here. Plus 6 times, and again the Laplace transform of y I am calling capital Y of s, and then the Laplace transform of e to the 4t is 1 over s minus 4. Okay. Alright, so putting in 2 for y sub 0 here, we have and then I'll combine the y of s terms. So we have y of s times the quantity s plus 6 minus 2, right? The y sub 0, y of 0 is 2, equals 1 over s minus 4. All right, then second step, right? Solve for y of s. Solve for that, what is the Laplace transform of little y? Well, that would be this. Y of s equals, I would add 2, then divide everything by s plus 6. So that's 1 over s minus 4 times s plus 6, and then plus 2 over s plus 6. All right, and then I'm going to take the inverse Laplace transform of this, and we'll get our solution. So y of t is, and then breaking it up with the linearity property, that's the inverse Laplace transform of this fraction. 1 over s plus 4 times, s minus 4, 1 over s minus 4 times s plus 6, and then plus 2 times the inverse Laplace transform of 1 over s plus 6. Okay. Now this one's easy enough, right? This would be e to the negative 6t, because it's s minus negative 6. I'm going to use partial fraction decomposition for this one. So 1 over s minus 4 times s plus 6, right, is some constant over s minus 4 plus some constant b over s plus 6. Multiplying through by the denominator, we'd have 1 equals a times s plus 6 plus b times s minus 4. Now if s were 4, the b term would go away. You'd have 10a equals 1, so a equals 1/10. And if s were negative 6, this term would go away. You'd have negative 10b equals 1, b equals negative 1/10. All right. So now bringing this down here, the y of t is 1/10 times the inverse Laplace transform of 1 over s minus 4, and then minus 1/10 times the inverse Laplace transform of 1 over s plus 6, but then I also have plus 2 over here, which is 20/10. Minus 1/10 plus 20/10 will be plus 19/10. Combining these like terms, and the inverse Laplace transform of 1 over s plus 6. And there we have it. We should know these. Here's the solution to our initial value problem. Y of t equals 1/10 times the inverse Laplace transform of 1 over s minus 4 would be e to the 4t plus 19/10, and then the inverse Laplace transform of 1 over s plus 6 would be s minus negative 6. That's e to the negative 6t. And there you have it. All right, and you can double check, take the derivative, substitute into our differential equation up top here. All right, substitute this stuff into the differential equation, and it should work out. And also, does it satisfy the initial condition? Yeah, when t is 0, you'd get 1/10 plus 19/10, so this is 20/10, so this is 2. And again, I'll leave that to you to verify, but this should be good. Okay. All right, so those are both first order equations. And the same stuff applies for second order. You just have to apply that Laplace transform of the nth derivative to more derivatives, that's all. So here's another example. So again, I know you could probably do, you could do this without Laplace transforms, right? But we're going to do it with. Right? Alright, so same three steps, same three procedure here. So I'm taking the Laplace transform of both sides. So we have the Laplace, and I'm going to use the linearity property on the left. So we have the Laplace transform of y double prime plus 5 times the Laplace transform of y prime plus 4 times the Laplace transform of y equals the Laplace transform of 0. Alright, so now applying that Laplace transform of derivatives formula, the Laplace transform of the second derivative would be s squared times the Laplace transform of y, which again I will call just capital Y of s, minus s to the first times little y of 0, then minus, and then y prime at 0. Okay. This is all the Laplace transform of the second derivative. Okay, plus 5 times, and then the Laplace transform of the first derivative, it would be s times y of s, right, capital Y of s, the Laplace transform of y, minus y of 0. Right, you've seen that in the first two examples. Then plus 4. Now the Laplace transform of y, again, I'm calling capital Y of s, equals. And then I hope you see, you could use a definition of Laplace transform to very easily see that the Laplace transform of 0 is 0. Right, it would be the integral from 0 to infinity of e to the negative st times 0. Well, that would just be 0 dt. Right? Okay. So now I'm going to put in these conditions, and we'll simplify some things. So y of 0 is 1, y prime of 0 is 0. So this is s squared times, capital Y of s. Y of 0 is 1, so this is just minus s. Y prime of 0 is 0, so that's gone. Plus, and I'll distribute the 5 here. So we have 5s plus 5s times capital Y of s. And then again minus, now y of 0 is 1, but I'm multiplying it by 5. So that'd be minus 5. Then plus 4 y of s equals 0. Alright, now I've got everything nice and written out here. Let's solve for y of s. Alright, so I've got y of s, right, the Laplace transform of little y, times the following. You have s squared plus 5s plus 4. And then, the terms without y of s attached, so let's take to the other side. So I'll add s, add 5. S plus 5. Right. Okay, and then divide by this. So we have y of s equals s plus 5 divided by s. Well, you know what? I'm going to factor this right now. S squared plus 5s plus 4 factors to s plus 4 times s plus 1. And what I'm going to do is actually now write out, I'll do the partial fraction decomposition, right? PFD, partial fraction decomposition. So this s plus 5 divided by, s plus 4 times s plus 1, I can write as a constant divided by s plus 4 plus another constant b over s plus 1. Again, that's only because these are linears. and then multiplying through by the denominator, we'd have s plus 5 equals, a times s plus 1 plus b times s plus 4. And if I were to let s be negative 4, you'd have 1 equals negative 3a, so a equals negative 1/3, and b would have to be equal to, now if s were negative 1, this side would have 4 equals 3b, b would equal 4/3. So this is negative 1/3 over s plus 4 plus 4/3 over s plus 1. Okay. Now let me just double check that real quick. Yeah, 4/3 for b and negative 1/3 for a. Okay. All right, and then I do the inverse, which are pretty simple again here. So far I've actually picked some pretty simple examples. So then solve. Take the inverse. Y of t. The inverse Laplace transform of the Laplace transform of y would just be y itself equals, and then negative 1/3 times the inverse Laplace transform of 1 over s plus 4. That'd be e to the negative 4t plus 4/3, and then times the inverse Laplace transform of 1 over s plus 1. That's e to the negative t, e to the negative 1t, and there you go. Here's the solution of that initial value problem. And again, you can verify that it is indeed a solution by taking the first derivative, second derivative, and substituting into the equation, and making sure also that they satisfy it satisfies the initial conditions. That y of 0 is 1 and y prime of 0 is 0. All right, so I've just got one more, another second order one, but this time I have a non-homogeneous equation for you. All right, so I'm going to say y double prime plus y equals the square root of 2 times the sine of the square root of 2 times t. Y of 0 is 10, y prime of 0 is 0. Let's find the function y of t that satisfies this. Alright, so Laplace transform of both sides. And do the Laplace transform of y double prime. Using the linearity property, I can just go term by term, plus the Laplace transform of y equals, and then using properties of Laplace transforms, I could pull the square root of 2 out here, and times the Laplace transform of the sine of the square root of 2 times t. Alright, so remember from last example, this is s squared times the Laplace transform of little y times y of s minus s times y of 0 minus y prime of 0. Right. And then this is just y of s, right? The Laplace transform of y, I'm calling capital Y of s, equals the square root of 2 times, now remember the Laplace transform of the sine of kt was k divided by s squared plus k squared, right, where k here is the square root of 2. And then having the two square roots of 2 in the top, make that just 2 over s squared plus 2. Okay. Alright, then just as before, I'm going to put in the conditions. Y of 0 is 10, y prime of 0 is 0. So this is s squared times y of s minus 10s, right, y of 0 is 10, minus 0, then plus y of s equals, this 2 over s squared plus 2. Okay, then we solve for y of s. This would be y of s times the quantity s squared plus 1 equals 2 over s squared plus 2 plus 10s, right, plus 10s. And then I divide everything by s squared plus 1. So we get the following for the Laplace transform of our solution, and then we need to take the inverse Laplace transform. So we have 2 over s squared plus 2 times s squared plus 1, then plus 10 times s over s squared plus 1. Now this one is an easy one to find the inverse Laplace transform for. It's this one that I need to do partial fraction decomposition for. All right. So let's do that. So I'm just going to write PFD for partial fraction decomposition. So 2 over, now these are irreducible quadratics. We have over s squared plus 2 times s squared plus 1 equals, now remember these are irreducible quadratics, so the numerator in their partial fraction decomposition, the numerator will be some linear expressions. So say as plus b, a linear, over s squared plus 2, plus, and then another linear, cs plus d over s squared plus 1. And then I multiply through by the denominators and we get the following. 2 equals as plus b times s squared plus 1 plus cs plus d times s squared plus 2. And then I'm going to get it to be combine some like terms over here. This would be what? as cubed plus bs squared plus as plus b. And then we have cs cubed plus ds squared plus 2cs plus 2d. Alright, so hopefully you can see that a plus c must be 0. Right, the sum of the coefficients of s cubed. There's no s cubed on the other side. B plus d must also be 0. A plus 2c must be 0. And b plus 2d must also be, must be 2, sorry. The coefficient, the constant terms must add up to 2. Okay, now notice that these two equations have just a and c in it. So you can see hopefully that a must be a is 0, c is 0. Right? That's the only way these two are both going to be equal to 0. Because a would be the opposite of c, then you'd have negative c plus 2c, which is 1c. C would be 0, a would be 0. Right? And then from these two, b would be the opposite of d. So negative d plus 2d is d. D equals 2, and b would have to be negative 2. Right? Okay, so what I'm getting here, after putting these constants in, I'm getting that 2 over s squared plus 2 times s squared plus 1 would be negative 2 over s squared plus 2 plus 2 over s squared plus 1. Okay. All right, and now I have everything I need to do the inverse Laplace transforms pretty easily. So again, rewriting this using the partial fraction decomposition of this first fraction. So we have negative 2 over s squared plus 2 plus 2 over s squared plus 1 plus 10 times s over s squared plus 1. All right, now taking the inverse Laplace transforms, those are all in some nice forms there. Y of t, little y of t, would be the opposite of the inverse Laplace transform of 2 over s squared plus 2. And the only reason I'm leaving this way is because we know what this is. All right, we know what this is. 2 over s squared plus 2 was the Laplace transform of the right side of our equation. So the inverse Laplace transform of 2 over s squared plus 2 is this, square root of 2 times the sine of square root of 2t. All right, so I'll write that in here. The negative, square root of 2 times the sine of the square root of 2 times t. All right, then we have plus, and then 2 times, I'm pulling the 2 out this time, the inverse Laplace transform of 1 over s squared plus 1. So this is in that form k over s squared plus k squared, where k is 1. And that's the inverse Laplace transform of the sine of t, the sine of 1t. So plus 2 times the sine of t. And then the last one, plus pulling the 10 out, 10 times the inverse Laplace transform of, you have s over s squared plus 1. And this has got that form s over s squared plus k squared, where k is 1. And that was the form of an inverse Laplace transform of the cosine of kt, or the cosine of 1t. So plus 10 times the cosine of 1t, or just the cosine of t. And there you go. There's the function y of t equals, negative 2 times the sine of the square root of 2t, square root of 2 times t, plus 2 times the sine of t, plus 10 times the cosine of t. And again, if you want to verify this, take the first derivative, take the second derivative, substitute into the equation. This should satisfy this equation and also satisfy, the initial conditions. Y of 0 is 10, y prime of 0 is 0. All right, and again, you can bump this up, do third order, fourth order, higher order equations if you wish, right? Just just the only time you're going to be able to use the Laplace transform, though, to solve initial value problems is if those initial values are at, initial conditions are the function and its derivatives evaluated at 0. All right. Okay. So hopefully watching me do these 4 examples help you out when you're working on similar problems on your own. And thank you very much for watching.